Hi everyone, today we are going to learn about instant insanity. To give a quick overview about what this topic is, we are going to learn how to stack 4 different cubes on top of each other so that one color is shown on each side, and we're going to solve the problem through graphs. So like I mentioned just now, how can we stack 4 cubes with different color faces on each side? Now that question kind of may sound a little hard to understand, but to visualize it, I have a picture. On the top view of the cubes, we have a blue side, a yellow side, a red side, and a green side. So that's what we're shooting for on all 4 sides. And then on the front side, we have a blue, green, yellow, and red. And assuming so on the bottom and on the other side, it's a variant of those 4 colors as long as those 4 colors show once. And to solve, we are going to solve with graphs. Before we can continue, it is important to know how to form the graphs. And to form the graphs, each color represents a vertex, and the edges represent the line that connects a face to its opposite side, and I'll explain that in a minute. These are the graphs, or these are the cubes that I used for the rest of the project. I found these and they're just easy to use. So I have a cube 1, cube 2, cube 3, and cube 4. And a little insight as to why it's called instant insanity is because this particular topic, there are so many different outcomes that you can get depending on how many colors are on per cube, how the colors are rearranged on the cube, what sides are used, what sides aren't used, since we'll be only focusing on 4 out of the 6 sides. There are going to be 2 colors that aren't going to be used. That's why it's called instant insanity, because trying to solve this without any math and just rearranging, it's going to take a lot longer than using graphs to solve. So with that said, looking at cube 1, I have made the graph to visualize how to start solving this problem. So for a reference point, I used yellow as the front for this graph. So if we look down here, so from left to right, we have red on our left and green on our right. So those two sides and 2 colors are opposites of each other, and that's what makes the edge that I have here. Bottom to top is red to red, and since red is opposite to itself, there's just a loop. And then front to back is yellow to blue, and that's what this edge is for. So this graph is just represented of what the cube, where the colors are on the cube, and the opposite side. So if you look at the second cube with yellow still being the front, left to right is red and blue, so those 2 are opposites. Bottom to top is yellow to red, and then front to back is yellow and green. So that's what this graph is telling us. We are able to visualize what the opposites are. And then quickly, this is graph 3 for cube 3. And this is cube 4. Now those are just 4 separate graphs for the 4 separate cubes, but we want to solve what the solution is for the 4 cubes stacked onto each other. So just like the cubes in the stack, we want to stack the graph to help solve this problem. So stacking all 4 graphs, this is what it looks like. Now, it looks like a lot because of how the graphs lay on top of each other. Each number represents like what graph it or which cube it's representing. So 1 is cube 1, 2 is cube 3, and so on and so forth. But this is a lot to look at, and with this kind of information, it is hard to figure out how to solve this problem. So to make it an easier way, we will make 2 different graphs. A graph that looks at the front and the back of the 4 cubes, and the second graph is going to look at the left and the right of the cubes. Now, this is where it gets a little tricky because, like I said before, we're going to be using 4 sides out of the 6 sides on the cube, so 2 are not going to be used. This is where the rearranging comes into play. And the front is not always going to be your front, and your left's not always going to be your right, or your left's not going to always going to be your left. So I picked random fronts for this particular example. I still stayed with the colored cubes that I have that we've been using, so that my answer is not going to be different. So if we look at the first graph, it's the front, we have a green, a red, a blue, and a yellow. So that works. We have one side that has one color on all 4 colors. If we look at the back, we have a red, blue, yellow, and green, and that works. So if we were only looking at the back and the front, this particular graph works. We have 4 colors showing up once on each side, front to back. But even though that works, we also want to look at our lefts and our right just to make sure. And even though this graph looks pretty similar to the first one, the front and the back, we can't assume that it works, the lefts and the right, so we have to go through it. So we have a yellow, a green, a blue, and a green. Since we have 2 greens on our left side, it doesn't work. This whole arrangement does not work, so we would have to rearrange our cubes and start over again. But even though the 2 graphs look similar, I will move on to the conditions and explain why they don't work. So we have 3 conditions that we need to look at when looking at the graphs. Each vertex should have 2 degrees. Each cube should be represented by an edge exactly once on each graph, and the 2 graphs should not have any edges in common. Now, going back to the graph, just looking at it, each graph does have 2 vertices. Each graph is represented by each edge once. There's a 1, 2, 3, 4 and a 1, 2, 3, 4, and each graph each edge wasn't shown up twice on the graph, meaning if this on the front and back, the red and the green is cube 1, that means that in the left and the right, the red and green can't have a number 1, because it just contradicts the cubes that we have. It could potentially work depending on how your cubes are formed, but with the particular ones that we have, it just doesn't work. So if we The reason why this doesn't work, and I didn't do this, so I'm sorry. If we look at the front and the back graph, this works entirely. We have two vertices coming out of each vertex. We have degree 2 for each vertex. Each edge is represented once, and we can't look at the third condition since this graph isn't correct, but assuming that it is, for the 1, 2, 3, and 4 is not in the same spot as the other graph. The reason why this one works is because if I had arrows, it would show that green is going to red. This vertex is leaving the green, and this vertex between yellow and green, this line is going into green, if that makes sense. So one edge should be leaving the vertex, and the other edge should be going towards the vertex. So if you look at the left and the right, the reason that this doesn't work, even though it satisfies most of the conditions, if you look at 2 and 4, we have the two edges coming out of red are going away from red. For this to work, we would need one to go towards red and one away from red. So the solution for this particular, these particular cubes it's gonna look like this. And I apologize that I didn't put arrows in. I didn't think about that, but I have my cubes. So it's gonna be yellow, green, blue, and red for my faces. So if we look, we have 4 colors. And if I turn it around, I don't have 4 colors. And if we turn it around, I have 4 colors and I don't have 4 colors. Did I do this wrong? I swear I did this correctly. Oh, I see what my problem is. I don't see what my problem is. I'm so sorry. But yes, that's the answer. I can't figure out my cubes right now. But that is instant insanity, how we use graphs to solve them. Each vertex is a color. Each edge is the connection between its opposite sides, and we have our 3 different conditions. So those are the main things that we want to look at in terms of trying to solve our 4 cube problem. Yeah.